Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we are going to be discussing heating and cooling curves. So a heating or a cooling curve is a plot of the temperature of a substance as a function as the heat absorbed, usually in kilojoules, but the actual unit doesn't matter all that much. So if you see this, you end up seeing kind of a stepwise plot. And the three different diagonal sections represent the three different phases of matter. At the lower end temperature, you have solid, liquid in the middle, and gas at the end. So what's happening in between are those phase changes. So we have very different chemistry happening on diagonal and horizontal lines. So we're going to talk about each one of these line segments, labeling them A through E. So starting with line A, this shows how the temperature, and therefore the kinetic energy, of the solid rises steadily as heat is absorbed by ice. We're talking about the heating curve of water, so I can call it ice right now. So we know temperature is a measure of kinetic energy. So as I'm adding energy, all that's happening is the molecules are taking that energy and converting it into kinetic energy. They're moving faster. It's still a solid, it still has the characteristics of solid, but the temperature is rising. Now, eventually, we're going to hit the melting point, which was where we get to line B. Line B shows how solid ice is converted into liquid water at the melting/freezing point. So this horizontal line indicates that the kinetic energy remains constant throughout the phase change. Now, if the kinetic energy is remaining constant, notice that the temperature remains constant throughout the phase change as well. So instead of the energy going towards raising kinetic energy, instead of moving faster, the energy is going into breaking intermolecular forces to go from solid to liquid. Now, eventually, all of the all of the solid molecules are going to be liquid molecules, which is where we get to line C. This shows how liquid water gains kinetic energy, so the temperature rises, until now the boiling point is reached. So on line D, at the boiling point, liquid water is converted to water vapor. This is another phase change that's happening. So the temperature remains constant throughout the phase change because the kinetic energy is remaining constant throughout the phase change. Now, eventually, all of the liquid molecules are now gaseous molecules, and we get to line E. This is where water vapor continues to increase in kinetic energy because the temperature continues to rise as the gas is heated. So you have solid, phase change, liquid, phase change, gas. So the diagonal lines, this ice, water, and steam, what's happening on these diagonal lines? You have one state, the temperature is rising, which means the kinetic energy is also rising. So the diagonal lines have similar chemistry. The horizontal lines, where we have ice and water, water and steam, are different. This is where phase change happens. So we have equilibrium between the two states. You have both ice and water at the same time. You have both water and steam. It's a conversion from one to the other. At these points, the temperature is constant because the energy is going to breaking intermolecular forces instead of raising temperature. So kinetic energy is constant. So the temperatures at which those phase change happens are the melting and boiling points respectively. So from the heating curve, you can actually tell me what the melting and boiling point is. So if you want the melting point, you would see where that horizontal line, and this is water, so it lines up at 0 degrees Celsius. The boiling point comes across at 100 degrees Celsius. So for any substance, looking at the heating curve will tell you the melting and boiling points. So here's a checkpoint question. It's asking what is the melting freezing point of this substance and what is the boiling point for this substance. So take a second, see if you can figure out on your own, and I'll reveal the answer in a moment. Did you get it? Looking at the melting and freezing point, you want the line between the solid and the liquid. So coming across, that is at about 1500 degrees Celsius. It depends how specific you were. I'm happy with 1500 degrees Celsius. Now, what is the boiling point? That's the line between liquid and gas. So coming across, if I estimate that, it's about 2750 degrees Celsius, somewhere in that ballpark. Okay, here's a more detailed heating curve for water. So you can see it says solid, liquid, and gas. It notes where the boiling point and melting points are. And it shows you two different arrows, melting versus freezing, boiling versus condensing. So if you're looking as you add heat, that is a heating curve. You go from solid, you melt, to liquid raising temperature, boiling, and then you're at gas raising temperature. If you were to go the other direction, that is what we call a cooling curve. The gas cools, so heat is now being released instead of added. It's an exothermic process. The gas is being cooled, it condenses, it's a liquid, it freezes, it's a solid with decreasing temperature. That's why it can be called a heating or a cooling curve. In fact, cooling curves can actually be drawn in a reverse image, so you could actually have it coming down here, across, coming down, and instead of being heat added, it would be heat released. But you can just think of going one direction or the other along the x-axis, and you have both within one diagram. So, heat calculations on a heating or cooling curve has two different energy calculations. During phase changes, energy is going towards breaking intermolecular forces, those IMFs, which means we're using molar heat of the phase change times either moles or grams depending on our units. Now, Q is just chemical notation for energy. It means the same thing as delta H. As temperature increases, so on those diagonal lines, energy is going into raising the kinetic energy, which means instead we're using MCAT, the mass times the specific heat times that change in temperature. Which means if we're talking about one energy addition, we might have multiple energy calculations. So, specific heat versus heat of fusion and vaporization. We've talked about this before. The heat of fusion or vaporization is the energy needed to change state. Specific heat is the heat energy needed to raise the temperature within one state. So, the heat of fusion for melting is down on that melting point. The heat of vaporization to boil is at the boiling point. And then specific heat is used on all the diagonal lines in between. So if you want to talk about total energy, the total energy is the sum of all the individual processes. So delta H total is the sum of delta H for each process. You can think about this as delta H1, the first line segment, plus delta H2, the second line segment. It doesn't have to be delta H's either. You could use Q total and Q1 plus Q2 because Q and delta H mean the same thing. So let's look at an example of what this would look like. How much energy is required to completely change a 4-gram block of ice at negative 10 degrees Celsius to liquid at 25 degrees Celsius? And it gives me the molar heat of fusion in joules per gram. So on my heating curve, I need to think about where am I starting, where am I ending, and what line segments do I need to calculate. So starting with a block of ice at negative 10 means that I'm down here, ice, so the solid, negative 10 degrees Celsius, and I want to end as a liquid at 25 degrees Celsius. So in between, I've got three line segments. So looking at the first one, that's raising the temperature to the melting point. The horizontal line segment is to melt, a phase change, and then the third line segment, I'm raising the temperature to 25 degrees Celsius. So my Q1, this first diagonal, is going to be an MCAT. Q2 is going to use the heat of fusion. I'll multiply by grams because the units of molar heat was in grams. And then Q3 is going to be another temperature problem using MCAT. So Q total is going to be Q1 plus Q2 plus Q3. So I need to do three calculations and then add all of them together. So looking at Q1 using MCAT, the mass I have is 4 grams. The specific heat of water I know is 4.18 joules per gram degree Celsius. And then for the temperature change, that line segment ends at 0 degrees Celsius, so my final is 0. I subtract my initial negative 10. So 0 minus negative 10 is, of course, positive 10. So when I multiply all these together, I get 167.2 joules. For my horizontal line segment, I've got the molar heat of fusion times grams. So 334 joules per gram times 4 grams gives me 1,334 joules. And then my third line segment using MCAT again, it's going to look the same just with different temperature values. So 4 grams, 4.18 joules per gram degree Celsius. My final temperature is 25. Where I started from on this line segment is 0. So that gives me 418 joules. So I'm going to add all three of these together. Notice how each one of these is in joules. Now when you're doing a phase change, it's not usually in joules. When we get molar heat, usually it's in kilojoules. So what would you do if you had joules, kilojoules, joules? You would just take this and convert it to joules. Or conversely, you could take the 2 joules and convert them to kilojoules. Doesn't really matter if the question doesn't specify, which my question doesn't. So leaving it in joules is easiest for me. So I'm going to take these three values and I'm going to add them together to get 1,919 joules. Now I'm going to tell you, we're not going to worry about significant figures for heating curve problems. It's a bit of a pain to carry it through all these calculations. So whatever I get, I am just going to leave as my answer and call it a day. So that concludes our lesson on heating and cooling curves.